Hello everybody and welcome back to Digital Integrated Circuits. I'm Professor Adam Teman of the EnICS labs at Bar-Ilan University, and today we'll be going over the Kahoot for Lecture 2, the manufacturing process. So, we have 11 questions today, and the first is, why do we call this field VLSI, Very Large Scale Integration? Is it because we are able to make very large chips? Because we integrate many devices on a single chip or wafer? Because we have been scaling the length for 50 years? Or because we couldn't think of a more confusing acronym? Well, the answer, of course, is the blue one. So, as usual, we'll go back to our lecture and see what I'm talking about. So basically, the VLSI process is similar to Gutenberg's printing process. So what Gutenberg defined was, instead of going out and typing on a typewriter each one of the letters needed to print a book or a newspaper or something like that, and then one copy of the newspaper would take a long time depending on the number of letters you needed, we would actually make some sort of a mold that had all of the letters we wanted to print on the page. It didn't matter if we had 1,000 letters or one letter or whatever, and then we build the mold like as you can see over here, and then in one single step we can print down all of the words and all of the letters onto a piece of paper in a very quick process. The same can be said about making colorful types of things in today's type of printing processes. What we do is we actually break down the color into four types of molds. One would be cayenne, magenta, yellow, and black. That's a CMYK process, and then we break down the photo into these four parts of the color, and we go and run the paper through those four types of molds, and we in the end get our full colorful picture. The same thing is done with a VLSI process. So we go and we make our photo masks that have each one have a single layer or a single step or a single part of our design. It doesn't matter if we have one transistor printed there or a trillion transistors printed there. It's still one single step that produces one part, or one, like one blue or one magenta or whatever part of the process. And then we go and we run our wafer through the process, and we get the billion or trillion transistors, or we get the single transistor, but it's only a single time step that it takes to do it. And that's what very large scale integration is. That's why it doesn't cost us extra amount of time linearly according to the number of transistors or devices we want to print, but it takes a certain single amount of time, and we can print an infinite number or whatever number we are able to print at that time, and that is what enables us to integrate so many devices on the same substrate. Okay, so basically a VLSI process is the ability to integrate many devices on a single chip or a wafer. Okay, so that's what the answer is to that one. Question number 2. Which of the following process step pairs is in the wrong order? Is it that we first make transistors and then we make metal layers? Is it that we first grow a field oxide and then we implant the source in the drain? Is it that we implant the source in the drain and then deposit the polygate? Or is it that we deposit metal in via and etch away excess metal? So this is a bit hard, but the answer is over here. And to go over it, I will again go the basics, the real basics of a process flow. Okay, so how does the process flow kind of work? And this is just a real high-level overview. Of course, during the lecture, I showed a more detailed overview of what happens, but this will kind of give us an idea of what we're going to do over and over again. So we start with a wafer, and the wafer is very big. It is not proportional to what I draw here, but this is going to be a very clean piece, usually of silicon. Usually, we really have intrinsic silicon that has no defects in it and no impurities in it, and then we do add some p-type impurity in it just so we can have a p-type substrate. What we're going to do there, the first thing is we're going to define our active areas by using a mask that we can help grow our isolation areas. So these guys over here are these thick oxide regions that really isolate between the active areas, which will be over here and over here. And that could be with, as we showed in the far past, it was a low-cost process, which kind of I show here with the bird's beaks. Nowadays, STI is almost used predominantly in most modern processes. Okay, so we defined our active areas by growing our field oxides, which isolate between them. The next thing we're going to do is we're going to define the wells, so we can go and diffuse or ion implant our impurities into the areas, and we can make this, for example, if this is N-type, we're going to have an N well over here inside a P substrate. And over here, we'll usually actually make a P well just to have better, better control over the impurity under there and get better transistors. But again, the P well is connected to a P substrate, so this is really an ohmic type of a contact. There's a short between there, whereas here we're going to have a p-n junction diode, which we can reverse bias and make sure we're isolated from the substrate. The next two stages are actually pretty interesting. We're not going to use a mask to define our gate. What we're going to do is we're going to cover the whole entire wafer with a gate layer. By the way, just the fact that I have these hills over here, that's not accurate. We're usually going to actually do some sort of a wafer flattening with a polishing with CMP to have everything be exactly the same height. But just this is to just show a nice kind of a picture. So anyway, what we're going to do is we're going to grow our gate oxide. And actually, in the past, this was one of the secret sauces of silicon. This is one of the reasons that silicon became the dominant type of material that was used, because if over here we have a silicon layer, all we have to do is oxidize it, and then we get silicon dioxide on top of it. And these two types of materials connect really well together, and we're able to make a very nice gate oxide, which is really thin. Remember in the lecture we said that these gate oxides, they get onto the order of 1 nanometer. So we're talking about a few atomic layers that we're able to grow over here. And even in the past, when we had very old processes and it was much thicker, we were still able to make this really nicely with very few impurities, because any impurity inside there is going to actually affect our VT and ruin our transistors. So one of the reasons the silicon really was dominant was because we were able to grow such a nice gate oxide. And what we do is we're going to grow it on this whole entire huge wafer in a very very uniform fashion. So we did that without any photo mask, and the next thing we're going to do is we're going to actually go and deposit our polysilicon layer, which is going to be used for our gate electrode. So again, this is done without any photo mask. We do it in a uniform way on the entire wafer, and we get a really nice layer of polysilicon on top of the really nice layer of silicon dioxide, which is going to be our gate oxide. And then what we can do is we can bring in our mask, and we can go and pattern where we want our gates to be. And by then etching away the pattern to get, we can etch away both the polygate and the silicon dioxide, and we get this sandwich type of a thing. So we have this self-alignment, which really defined our gate. We didn't have to have two different masks, which, if one of the masks was patterned over here and one of them was over here, we'd have a bad overlap between them and some excess areas on the side. But because we did it together, we got, this nice patterning. This is a self-aligned type of process, and self-alignment is really what we use to define any of these very small features and so forth, especially in our really advanced processes today. So we want to use self-alignment as much as possible. In fact, our next step is also using self-alignment. So we want to implant our source and drains, and we want to make sure that we hit the areas that, we don't accidentally dope underneath the channel, because that's going to change our VT and so forth. But here, look, what we did is we shot, with ion implantation, our ions on top of the wafer, and anywhere that actually wasn't covered is going to be doped with it. Over here, it's going to be P+, and over here, it's going to be N+. And that's fine, because if it hits this area, it's going to get stuck in the oxide, in the FOX, in the field oxide. If it hits over here, it's going to be stuck inside the polygate. And actually, diffusing implanting some ions into the polygate is actually used to set the threshold voltage a bit better. So that's often used. They can also be covered, but it doesn't matter if they're perfectly covered, because in any case, the stack of the poly and the oxide is going to protect our channel from being protecting from getting these impurities, which would really ruin it. It could ruin our transistor. Only in these areas, really, we're not going to have any protection, and these ions are going to be directly implanted into there. And remember that when we do such a thing by implanting ions into our silicon, it's going to ruin our crystal. It's going to make it ugly, and we don't like ugly things. So we heat up the wafer, and these things will anneal and fix the crystal, and it'll be really nice. That will cause some diffusion, so this guy is going to get bigger and so forth. So these are things that we have to take into consideration when doing this processing. So again, the implanting the source and drain is again going to be using this self-aligned type of a technique. Okay, after we do that, we can start doing our back end. Actually, nowadays we call this a middle end of the line, but in past processes, which I'm talking about at this point, what we usually do is we call this part the front end of the line. And that's the transistors. Building the transistors is really complex. It takes a lot of steps, many photomasks. In fact, today it would be hundreds, possibly even close to 1,000 photomasks just to make this front end of the line. Maybe not to the point of thousands, but really a lot of masks and process steps. Whereas when we go up here, we're talking about the back end of the line. Again, nowadays we're also talking about these layers that contact to the gates and to the source and drain. We call them middle end of the line. But in the past, it was all back end of the line. And what we do is we throw down these, tunnels, these connectors that go and they connect to the source drain and to the gate regions. And we call those guys contacts. So these are contacts. Okay, and they contact to, again, to our transistors, to the source and drain areas and to the gate areas. And we have our oxide that really disconnects between them, and that's called an interlayer dielectric. Okay, so that would be our contact layer, and then we're going to polish away the interlayer dielectric and make our next metal layer on top, which is going to be, our like metal 1 layer. And we can pattern that, and then again put our grow some interlayer dielectric around that to isolate between the different metals, and put another metal type of thing on top, and this would be our metal 2 layer. And voila, we get our CMOS inverter with this kind of funny type of a cross section over here. But just to show you, what we have here is really, this is our in. Our V in, this would be our out terminal, this we would connect to VDD, and this we would connect to ground, and we really get our transistor, our inverter over here, that looks something like this. This is an NMOS, this is a PMOS, this is in, and this is out. Okay, so that's basically our CMOS process. So let's go back to our Kahoot question and see why that was the right answer. So which of the following process pairs is in the wrong order? Do we first make transistors and then make the metal layers? Yes, this part is the front end of the line, and this part is the back end of the line. Do we grow the field oxide and then implant the source and drain? Yeah, we saw that growing the field oxide is isolating between the active areas, and that's something we do like really early along. And later on, we implant the source and drain in a self-aligned type of process around the gates. Okay, do we deposit metal in via and then etch excess metal away? And yes, what we do is we first do the deposition and then we etch away the metals. But do we implant the source and drain and then deposit the polygate? No, we first make the polygate and use actually the self-alignment of it to then implant the source and drain. So this is the wrong answer, which in the case of this question is the correct answer. Mark the incorrect definition. STI is the process of growing a field oxide that leaves bird beaks. Annealing is heating up the wafer in order to fix bonds. Diffusion is the movement of dopants due to heating. RDF is the random distribution of dopants in the channel. So which of these is incorrect? Well, I think it's going to be this one. So again, let's just look at that and then discuss the other things. So field oxide, we said that there's the low-cost process and the STI process. And actually, low-cost is the one that creates these bird beak type of things that are a real big problem. Another problem we said that we could have is that we really have this type of an M, because we're going to have like a metal 1 layer over here, and then we have this big oxide over here, and then we have the substrate over here, so we get this transistor. And this is not a transistor we want. Remember, this whole area is made to isolate between transistors, and here we can actually turn on, some sort of source and drain beneath over here and make a channel. So what we want to do is really put an implant over here that will make it the threshold voltage of this type of parasitic device really high and never turn on. So we're going to show how to do that with the STI process, the shallow trench isolation process, which is really predominantly used in today's processes. So we're going to start with patterning of the active areas and blocking them with some sort of a blockage layer. And then we're going to go over here and we're going to etch away really everything that's not blocked, and we're going to dig a trench inside the substrate. So we really dug down inside, and then we can go and deposit, we can implant our field implants that are going to cause the VT of this parasitic transistor that's going to be over here to be really high. And then we can go and deposit oxide, and it becomes much more anisotropic, and we get a much more pretty type of a isolation without these bird beaks that would cause us to have larger spacing requirements between diffusion areas. Okay, so that's basically what we get, and you can see over here that we get this nice shallow trench isolation. So STI is not the process of growing a field oxide that leaves bird beaks. That is the low-cost process. What about the other answers over here? So annealing is heating up the wafer in order to fix bonds. So yes, exactly, that's what it is. So again, when we do things like ion implantation, we're going to hurt the crystalline structure, which should be really nice to get very well-controlled, processes and so forth. So when we do that, what we have to do is heat up the wafer to a really hot temperature. That gives the atoms, the atoms of the silicon crystal a lot of energy, and then they can go and move around and find their lowest energy point, which is the nice, beautiful crystal we had before. That whole process is called annealing. It's a really important process. The only problem with it is due to the high temperatures that it requires. First of all, it causes diffusion, which we have over here. Diffusion is the movement of dopants due to heating, which isn't always what we want to do, and we have to take it into account. But the other thing is it can ruin other things that we already have produced in our process, such as metals, which may melt at a lower temperature than the annealing. So annealing is really important, but it can be problematic. Okay, RDF, or random doping fluctuation, is the random distribution of dopants in the channel, and that's exactly what it is. So actually, when we make our transistors, what we're going to do is we're going to add some dopants underneath the gate where the channel area is, and these dopants are going to cause our VT to shift. The problem with that is that at really scaled processes, we get 100 or even fewer dopants. And when we take some sort of a random, statistical process of shooting dopants into a channel at a certain depth, and we want to get some sort of a type of amount of dopants into there, that's not going to be exactly 100 or 95 dopants or however many we wanted. It's going to be a bit more or a bit less, and that bit more or a bit less can cause really hard fluctuations in our VT, and that is really the main cause of process variations in nanoscaled planar technologies. Okay, so going to our next question, what is a deep NWEL used for? And is it used to provide a separate body bias for NMOS transistors? Is it used to isolate devices from noise in the substrate? Is it used to create special devices such as BJTs and diodes? Or are all of the above correct? And actually, the answer is that all of the above are correct. So let's go and remember what a deep NWEL is. Okay, so in a previous course, or usually we say you cannot change the body voltage of the NMOS transistor, and that's not really true. Actually, we use triple well processes these days, and the thing is that if you do want to change the specific body voltage of an NMOS transistor, it costs a lot of area, and so we don't usually do it for a standard digital transistor. But the way to do it, as you can see over here, is that we have our NWEL over here. We have and we're going to make our NMOS transistors by putting P+, and we're going to put an N+ and connect this, to VDD. This is going to be our substrate, so somewhere over here we would have a P+ that's connected to ground, and that's going to cause this to, the whole thing to be at ground. And this is fine because we get this diode, which is now going to be reverse biased, and it's going to be isolated, and that's fine. And then we have our isolation over here using our STI. And over here we have the same thing with a PMOS. So we're going to put an N+ and an N+ over here. We get our transistor. We're going to put a P plus over here and connect this to ground, and that's fine. There's an ohmic connection over here. Remember, this is already at ground because we have these well taps, for example, over here. And so everything is okay over here, and this is isolated. But we want to make a transistor over here that's going to be an NMOS with a different body bias. So we're going to put two, N pluses over here. We're going to get our nice transistor over here. And we want to actually stick a P plus over here that is connected to some sort of VB, which is not ground. But if we had just done it, over here, we're going to cause a short. We don't want that to happen. So what we do is we put a deep N well over here. So we put N type material really down here at this level. This is our deep N well. And then we make regular N wells over here. This is our regular N well. Okay, and this is our regular N well, which is exactly the same as we have over on this side over here. And now we can put N plus over here and put this, at VDD. Okay, and what that's going to give us is we're going to have a diode over here, which is going to be reverse biased as long as VB, is lower than VDD. And we're going to have another diode over here, which again is going to be reverse biased. So everything is okay, and now we can put whatever VB we want over here. What we use deep N wells for is, one thing, it's okay to change the body bias of a transistor, but usually the main reason to do it is to isolate certain devices or a certain area from all the noise that's going on in the substrate because of all the digital cells, especially that are toggling, that they keep, driving current all over the place, and that causes a lot of noise. And especially if we have like analog type blocks that are sensitive to noise, we want to isolate them from that. So we use this for isolation, as you can see over here. Okay, and there we can actually have the area cost, because analog devices and analog areas tend to be big anyway. How do we do this? So we have an NMOS device over here. Again, that's this NMOS device that we have here. And we have some sort of a contact, which is this P plus over here. Okay, and we want it not to be at ground, but at VB, as we can see over here, right? VB. Okay, so what we do over here is we first of all put the deep N well layer, and again, we're looking from the top over here at what we have a cross section on this side, and we need this to be all over the place. So you see, the whole thing is the deep N well. It has to be the bottom of the swimming pool. It has to be all the way underneath. And then we need these side wells over here. So that's really putting on all the side. We have the walls of the swimming pool, and they're going to be a N well layer, a regular N well layer. And then what we have to do is we have to contact this and connect it to VDD as we have over here. So we put a bunch of contacts. We could actually put a guard ring around the whole thing to provide even better isolation and connect those to VDD. So going back over here, again, the deep N well is used to provide a separate body bias for NMOS transistors, so that's one thing we can do. The second thing is we can isolate devices from noise in the substrate, and we can also do other things that we don't really discuss here in this course, but we can create special devices like bipolar junction transistors and diodes, also using a deep N well layer. We have, again, we're able to make these PN junctions, which are often needed. Okay, so question number 5. How do we create 7 nanometer transistors with a 190 nanometer laser? Now, we're supposed to find the incorrect answer, and this type of a machine is one of the ways we do it, right? Okay, so number 1, using immersion or wet lithography, using phase shift masks, using extreme ultraviolet lithography, and using multiple exposures. Remember, I'm asking how to create 7 nanometer transistors with a 100 nanometer laser, and I'm saying most of these are correct. One of them is incorrect, and the incorrect one is actually the yellow one over here. It's not that we don't use extreme ultraviolet lithography, as we said we do, but extreme ultraviolet lithography is a 13 nanometer laser, not this 193 nanometer laser. All the other ones are ways that we are able to use a 93 nanometer laser to make really, really small transistors. Okay, so let's go back to our slides over here, and as you can see here, we have this really important equation that talks about the critical dimension, and this could be called CD or D. It's the really the resolution of our lithography. and it has some sort of a constant. It has the wavelength, and we said the wavelength is given in this question to be 193 nanometers because for several decades we use, and many process variations, this is the laser that we used. So that's set at 193 nanometers. And now what can we do? So this n really is the refraction coefficient of the substance that we're shooting our laser through. And usually we use air, which is 1, but instead we'll use immersion lithography, which means we put water over here, and that will cause us some sort of to get a smaller factor over here. The sign alpha, and what is that exactly? It's this together is the numerical aperture of the lens. To get a big alpha over here, what we need is a huge lens. And as you saw the picture on the Kahoot question, we really have a big machine. A lot of that machine is actually the lens, which has to be really big and heavy and huge and expensive to make a large sine alpha. But actually, in the end, in the end, what we can do is we can get about an 80 nanometer pitch. 76 nanometers usually is the minimum pitch we can get. Some of the ways to do it is, for example, with phase shifting. So we use two masks or two types of slits that have different phases in them, and we can use kind of refraction to help us get better pitches. But what we had to do actually when we went to deeper technologies, we started to use multiple patterning. So that means we use several masks and we just shift between the masks, or we use self-aligned double or quadruple patterning, which is something that I'm not explaining probably much in this course. But that is what we actually do in processes such as 16 and 7 nanometers to get really close-based pitches. By the way, 7 nanometers is not something that's actually made necessarily. Maybe the fins are at such a pitch, but most of the things are really patterned up to like gate lengths would be something like 14 to 16 nanometers in even a 7 nanometer process. So the number is mainly a number for marketing. It's not actually what the critical dimension is anymore in these processes. However, it is much smaller than 193 nanometers, and it's pretty amazing how we're able to achieve this. That being said, it costs a lot. We need a lot of masks to do it. A lot of masks means a lot of expense, a lot of time, a lot of variation, problems with alignment and so forth. And so really we were finally able at 7 plus, TSMC 7 plus, or at the different 5 nanometer processes to change over to the EUV 13 nanometer laser, and that's what is currently being used for the most advanced processes. And that really enables us to reduce the number of masks by a very large amount, and also to get less variation and less alignment problems and so forth. So going back here, we use wet lithography, we use phase shift masks, and we use multiple exposures, all with 193 nanometer laser. And then the next step is really to get a 10x reduction by going over to extreme UV. But again, you should know that these other techniques are in some ways being used or will be used in the future with extreme ultraviolet lasers as well. So question number 6, which of the 3-letter word definitions is wrong? ILD is interlayer dielectric, EUV is extreme undervoltage, CMP is chemical mechanical polishing, or OPC is optical proximity correction. And of course, extreme undervoltage is not a real acronym. As we said before, EUV is extreme ultraviolet. Okay, so we know that one's wrong. What are the other ones? ILD, as we said, is the interlayer dielectric. That's the silicon dioxide, or now we use different materials that have a even lower dielectric constant to separate between the metal layers and between the vias and so forth. So that's the ILD, and we'll be using that word very often during this course. Okay, CMP, chemical mechanical polishing, that's a step that's done between almost every step or every layer we do, and it's taking our wafer and using both a chemical, wet process and a mechanical, actually like polishing our wafer to get it to be really cleanly polished, to get it to be a perfect mirror. So every type of step starts with everything being at the same height and being very uniform. OPC, or optical proximity correction, is when we take our the rectangles that we drew in our layout, and we know that due to refraction and all kinds of other physical properties, it's not going to come out and make perfect features like that. So we go and we add all kinds of little nooks and crannies to our nice rectangle that we drew in the layout, and that will make our final design be more closer to what we actually drew. And that's something that's done after we tape out, before making the masks. Is algorithms that are run, they put on these different OPC type features, and then that's what's actually printed on the photo mask. Okay, so that was those definitions. Question number 7. Which of the following is not a cause of global variations? Fab-to-fab variation, wafer-to-wafer variation, die-to-die variation, or transistor-to-transistor variation. So which of the following is not a cause of global variation? Well, that's going to be transistor-to-transistor variation. And let's go back to our slides to understand that again. So as we mentioned, there are different types of process variation. One is random variation, okay? Random variation occurs without regards to the location and patterns of the transistors within a chip. So RDF, or random dopant fluctuation, is the best known of these local type of variations, and really causes two transistors that are right next to each other to have different threshold voltages or different properties. But other things can also happen. For example, we have different line edge roughness or line width roughness, because just little small variations that happen when we process things, and it can really have a difference between two adjacent transistors. It's not something systematic. It's not something across a large area. Okay, systematic variation usually is something much, due to some sort of a location and patterns. For example, the density of the metals in a certain area will cause differences in how our CMP works and can cause all kinds of dishing and other problems. Or the distances we have from the well will cause different types of implants, because, ions will knock off the blockage layers and so forth. The distance to the center of wafer, so where our chip is relative to the radius of the wafer, these types of things will maybe cause some sort of systematic variation, which we can pre-measure. We can know how it's going to be, and we can see it affects like different areas or different chips separately. So we usually divide our whole pattern, our whole modeling, into two different things. One is intra-die or within die variations. Those are local variation, and those are completely random variations. So they're a variation between elements in the same chip. So that's local variation that things like RDF cause. So we have two transistors that are sitting right next to each other, and they're going to have different properties if it is VT or if it is length or width or so forth and so on, even though they're right next to each other. And then we have the inter-die or die-to-die variation, which we call global variation. And these are variations between chips in the same wafer and different wafers, or made at different fabs and so forth and so on. And these global variations, we assume that they occur to all of the devices that are on the same chip. And we actually usually model this in what we call a process corner. So going back to our Kahoot question, fab-to-fab variation, wafer-to-wafer variation, die-to-die variation, they affect all of the devices that we have in a certain circuit. So those are global variations. And usually, again, we use a quarter model to really model this type of thing. So we provide a model that has these built in to the variation built into it, and it affects all the transistors in our simulation. However, transistor-to-transistor variation is a random type of effect that will, if we have two transistors, we'll use usually what we call Monte Carlo simulation, which means we kind of roll the dice for each of the parameters, and according to a distribution, which will usually be a Gaussian distribution, we'll choose what the actual value of a certain parameter will be before we run our simulation. Question number 8. How many dopant atoms are there in a 28 nanometer transistor channel? Are there approximately 100, 1,000, 10,000, or 1,000,000? And actually, the surprising thing is we're talking about approximately 100 dopants. So going back to our slides, we discussed random doping fluctuation, and we see these types of plots that have been published, and you see that there's variation really around the channel in the amount of dopants we have here. And if we look at technology nodes, the average number of dopant atoms that we have in a channel has gone down, from the millions really across technology nodes, and now when we're in the low planar nodes at like 28 nanometers or something like that, we're really getting into the 100 or less than 100 dopants that we have inside our channel. In fact, at these types of technologies, we don't actually use doping anymore. We use what we call an intrinsic channel or a fully depleted channel due to this problem. The number of dopants, if we have only 100 dopants in the channel and we have a plus minus 10 atoms that it fluctuates or more than that, we're going to have a huge difference in our VT, and this is going to be such high local variation that it's going to be hard to design chips. So that's one of the reasons that we really moved to a fully depleted channel that doesn't have any of these dopant atoms inside, and it causes RDF to basically disappear, and it's almost non-existent. So this is a real big problem, and it's pretty amazing that we actually have been sticking only a few dopants, like hand picking them and sticking them into the channel, but it really wasn't sustainable, and so we actually stopped doing that at more nanoscaled devices and in FinFETs. Okay, question number 9, what causes electromigration? Is it electrons hitting the silicon during ion implant, negative voltages applied to a transistor, strong current flowing through a small conductor, or low density of metal deposited on top of an ILD? So with all of these, I'm going to choose the yellow one over here. So let's go back and see what electromigration is. So hilloking is something we don't discuss often. We usually just categorize it as part of electromigration. There are two phenomena that are reliability phenomena, and we usually just mention EM or electromigration as both of them. And the thing with electromigration is that we have electrons that are flowing through the channel over here, and the electrons, while we have current flowing, they're hitting the atoms, and eventually, they have some sort of mass. They're hitting the atoms, they're moving them a tiny little bit, and if we do this for long enough and for a strong enough amount of time, they're going to hit a certain atom enough amount of time so it gets displaced and moved. This eventually will cause a break over here, which will increase the resistance and finally cause an open circuit or something like that. It can also move the material into the interlayer dielectric and cause a short. That's what we would call a hillock. So there's a real big problem, and what causes it is, again, when we have current flowing through an conductor for a long amount of time and a lot of current. And the more current, the more possibility that the electrons are going to hit and move a certain atom. And so it's the probability is dependent on basically the current density. So what we want to do is we want to keep the current density in a conductor under a certain limit, and then we're going to be fine, which means we're going to use wider wires or something like that. So how do we keep away from electromigration? We're going to make sure we don't have that much strong current flowing through a small conductor for a long time by making the the resistance low, making the conductance real high, and that way we reduce the current density. Okay. The other things were just kind of wrong. Electrons hitting the silicon during ion implant. No. Electromigration is a reliability problem during operation. It's not a problem during manufacturing. Negative voltages applied to a transistor, well, that will also cause all kinds of problems, but not necessarily electromigration problems. And low density of a metal deposit on top of an ILD, again, that's something that's a problem that has to do with the CMP, but that's during processing. So the only one that's right is strong current flowing through a small conductor. Question number 10, how do you fix antenna violations? And again, mark the incorrect answer. By adding a diode connected to a transistor gate, by putting guard rings around the affected area, by making sure only short wires connect to small gates, or by breaking a long wire by jumping up to a higher metal. And the answer over here is going to be by putting guard rings around the affected area. So again, I will jump over to the slide where I discuss what the how to fix antenna violations. So the problem with antenna violations is that during manufacturing, so as opposed to electromigration, which was an aging problem, it happens, when we use the device for a long time and put a lot of current through it. This is a problem during manufacturing. During manufacturing, when we deposit a metal layer, we're going to have charge built up on the metal layer, and the charge, if we have this case over here, for example, when we made metal 3 over here, this is a huge piece of metal that is not connected to anything, but it's floating between all kinds of interlayer dielectrics. Remember, we made this and then this and then this and then this. Once we made this layer and these top layers do not exist yet, there's going to be a lot of charge in here. And if we then have, if we make another layer, for example, we make some sort of connection between these two guys over here, right? So if we make some sort of connection like that, all the charge that is over here, which builds up a large voltage, is going to go and look for a way to discharge to ground, and it's going to see this real thin oxide. Remember, we can get up to like 1.2 nanometers over here, and it's just going to break it like going through a fuse. Well, we don't want that to happen, because then this gate would disappear and we'd be in real trouble. Our chip wouldn't work. So how are we going to save that? So the first way to save that is by making sure that we have some sort of a reverse biased diode over here. So we have, on this case, we put a diode on purpose over here. We just put an N+ diffusion, which sits in a P in a P well over here, in a P substrate, and this is a reversed biased diode. And once we get this high voltage, so we have whatever 10 volts or more than that, it can be 100 or 1,000 volts or whatever that happens over here, depending on the amount of charge, it will just reverse break down this diode, and the current will dissipate to ground, and there's no problem with that. It doesn't break anything. This is just a junction breakdown, and that's the type of a fine thing that can happen for a short amount of time in this type of diode. At all other times, this diode doesn't bother us. It does have leakage through it, and it does take up some area, so we don't like to stick them all over the place. But as long as we put this type of a reverse bias diode near one of these problematic gates that has a big piece of metal that's going to be over it, then that's called an antenna diode, and that will solve our problem. But it's easier to just make a bridge. So what we have over here in this solution is that instead of connecting this over here, what we did is we broke this connection. So now when we made metal 3, nothing happens because all the charge is still stuck inside this piece of metal over here. Now we made metal 4, so we have this and this. This is, all shorted together, but we still don't have any connection to the gate because we haven't yet made this top metal over here. On the other hand, on this side, we did produce this metal over here. So now we created a connection to this reverse bias, this diffusion. There's a transistor over here, okay? And this was the source or the drain of that transistor. And we got our diode's going to discharge all the current because it's going to reverse breakdown, and that's fine. Now there's no charge over here, and now when we connect this, nothing's going to go and break this gate. So that's called bridging. So that's the other real way to solve the problem. So going back to the Kahoot, adding a diode connected to a transistor gate, these are these antenna diodes. They're a standard cell that we have in our library, and that's one thing we can do. Okay, making sure only short wires to connect the small gates, well, that's actually the check that we do. Our DRC run will check that there are no long wires that are connected to gates during a certain stage of the process, and then we will make sure we don't have antenna problems. But if we do find one, then we can either connect the transistor or break the long wire by jumping up to a higher metal. We call that bridging. The wrong answer over here is by putting guard rings around the affected area. The guard rings are used for different types of things, but not for solving antenna problems. So coming to our last question over here, why do we need to add well taps? And the answers are to eliminate antenna violations, to ensure VDD and ground are delivered to the CMOS gate, to reduce the chance of latch-up, or to reduce the effects of electromigration. So what do we use well taps for? And the answer is to reduce the chance of latch-up. So again, going back to our slides, I want to remind you what latch-up is. So we have all these P and N areas inside our CMOS type of a structure, and this causes a lot of these NPN type of structures or PNP structures, which are a bipolar junction transistor. So what we get over here is different types of circuits, such as the circuit over here. And this is completely parasitic. We didn't want it, so this is a parasitic NPN, and this is a parasitic PNP. And because there is a distance between where, this P, for example, connects to the substrate, it connects ground to the substrate, and, where, for example, this base of this NPN is, we have some sort of a parasitic, again, resistance between the two of them because the substrate has a rather high resistance. And then if something charges up this area and causes a voltage to appear on this guy, it will turn on the NPN over here. Turning on the NPN over here will cause a charge to appear inside this type of a resistor, which will cause a voltage over here, and turn on this PNP over here, which will again cause current to come over here and keep this voltage high, and we then get this strong current over here, strong current over here. The voltages keep ramping up, and it will basically blow out our chip. That's called latch up. Okay, we don't want that to happen. The way to not allow that to happen is make sure that these transistors never turn on. How do we make sure they never turn on? Make sure that the voltage never rises here. How do we make sure the voltage never rises here or here? We make sure these resistors are really, really small. And how do we do that? By just making sure that, at many different places over here, we tap them to the voltage they're supposed to be. So we make sure that at as many places as possible, we connect this to ground and we connect this to VDD. Okay? And when I say in as many places as possible, usually the DRC is something like every 30 microns, we have to provide a tap in order to make sure that our resistances will be really small between different areas inside our wells. Okay, so that's what latch up is. The other answers over here to eliminate antenna violations, we just discussed that. It has nothing to do with what I was talking about. To ensure VDD and ground are delivered to the CMOS gate, we use rails for that. It has nothing to do, again, with well taps. And to reduce the effects of electromigration, again, electromigration, we use wider wires or things like that. We don't, or better materials such as copper. We do not have anything to do with well taps. What it is used for is to reduce the chance of latch up. So that was it for the Kahoot for Lecture 2. And if you have any questions, you should ask me on my YouTube channel or write an email to me, and I'm available to answer them. Thank you very much.